Welcome to our exploration of digital computer organization, focusing on the essential functional units that make modern computers tick. In this video, we'll break down the core components inside a digital computer, revealing how each unit contributes to the overall operation. Whether you're a student, a tech enthusiast, or just curious about how computers work, this journey will give you a clear understanding of the building blocks that power everything from your laptop to massive servers. Let's start by understanding what functional units are and why they're so crucial in computer architecture. Functional units are the distinct blocks within a digital computer that carry out specific tasks. Think of them as specialized departments in a company, each with its own role. These units work together seamlessly to execute instructions, process data, and manage communication. By dividing responsibilities, computers achieve efficiency, speed, and reliability. In the next scenes, we'll look at each major functional unit, starting with the heart of the system, the Central Processing Unit, or CPU. The Central Processing Unit, or CPU, is often called the brain of the computer. It interprets and executes instructions, performing calculations and making decisions at lightning speed. The CPU coordinates the activities of all other functional units, ensuring that data flows smoothly and tasks are completed efficiently. Without the CPU, a computer would be unable to function, as it is responsible for running programs and managing system resources. Within the CPU, the Arithmetic Logic Unit, or ALU, is responsible for all arithmetic and logical operations. Whenever a computer adds, subtracts, compares numbers, or makes logical decisions, the ALU is at work. It handles basic calculations and complex operations alike, making it a critical component for data processing and decision-making within the CPU. Another key part of the CPU is the Control Unit, or CU. The CU directs the operation of the processor by fetching instructions from memory, decoding them, and coordinating the actions of the ALU and other units. It acts like a traffic manager, ensuring that every part of the computer knows what to do and when to do it. The memory unit is where data and instructions are stored, both temporarily and permanently. It provides the CPU with quick access to the information it needs to execute programs. Memory is organized into different types, such as RAM for temporary storage and ROM for permanent instructions. The efficiency of the memory unit directly impacts the speed and performance of the entire computer. The input unit is the gateway for data entering the computer. Devices like keyboards, mice, and scanners send information to the system, which is then processed by the CPU. The input unit converts user actions and external data into a form the computer can understand, making interaction possible. After processing data, the output unit presents results to the user. Monitors, printers, and speakers are common output devices. The output unit translates the computer's digital information into a human-readable or perceivable form, closing the loop of communication between the user and the computer. The system bus is the communication highway connecting all functional units. It carries data, addresses, and control signals between the CPU, memory, and input-output devices. A fast and efficient system bus ensures that information moves quickly throughout the computer, preventing bottlenecks and improving performance. Registers are small, high-speed storage locations within the CPU. They temporarily hold data and instructions that are being processed. Because registers are so fast, they play a vital role in speeding up computation and ensuring the CPU operates efficiently. Cache memory is a special type of high-speed memory located close to the CPU. It stores frequently accessed data and instructions, reducing the time the CPU needs to fetch information from main memory. This small but powerful unit significantly enhances processing speed and overall system performance. Main memory, or RAM, is where the computer temporarily stores data and instructions that are currently in use. RAM is volatile, meaning its contents are lost when the computer is turned off. The size and speed of RAM directly affect how many programs you can run simultaneously and how quickly your system responds. Secondary storage refers to devices like hard drives and SSDs which store data permanently. Unlike RAM, secondary storage retains information even when the computer is powered off. This unit is essential for saving files, installing software, and keeping your data safe for the long term. Input-output controllers manage the flow of data between the CPU and peripheral devices. They ensure that input and output operations are handled efficiently, allowing the CPU to focus on processing tasks. These controllers are vital for smooth communication with devices like keyboards, mice, and printers. The instruction cycle is the process by which the CPU fetches, decodes, and executes instructions. This cycle is repeated millions of times per second, enabling the computer to perform complex tasks rapidly. Each functional unit plays a role in this cycle, ensuring smooth and efficient operation. Data pathways or data buses are the channels through which information travels inside the computer. These pathways connect the CPU, memory, and input-output units, allowing data to move quickly and efficiently. The width and speed of these buses directly impact the computer's performance. The address bus carries the addresses of data and instructions between the CPU and memory. It tells the system where to find or store information. The width of the address bus determines how much memory the computer can access, making it a key factor in system capability. The data bus is responsible for transferring actual data between the CPU, memory, and other units. Its width, measured in bits, determines how much data can be moved at once. A wider data bus means faster data transfer and improved overall performance. The control bus carries control signals from the CPU to other components, coordinating their actions. These signals include read-write commands, interrupt requests, and clock signals. The control bus ensures that all parts of the computer work together harmoniously. All functional units are interconnected, forming a complex network that enables efficient data processing. The design and organization of these connections are critical for system performance, reliability, and scalability. Modern computers use sophisticated architectures to optimize these interconnections. Most digital computers are based on the von Neumann architecture, which uses a single memory space for both data and instructions. This design simplifies the system and allows for flexible program execution. However, it can also lead to bottlenecks known as the von Neumann bottleneck, when both data and instructions compete for memory access. In contrast, the Harvard architecture uses separate memory spaces for data and instructions. This allows simultaneous access to both, improving speed and efficiency. Many modern processors use elements of both architectures to balance performance and flexibility. Common input devices include keyboards, mice, scanners, and microphones. Each device converts physical actions or signals into digital data that the computer can process. The variety of input devices allows computers to interact with the world in many different ways. Output devices such as monitors, printers, and speakers present processed data to users. Monitors display visual information, printers produce hard copies, and speakers output sound. These devices make it possible for users to receive and interpret the results of computer operations. Firmware is specialized software stored in read-only memory that controls hardware functions. It acts as a bridge between hardware and higher-level software, ensuring that devices operate correctly. Firmware updates can improve performance and add new features to hardware components. Peripheral devices are external components connected to the computer, such as external drives, webcams, and game controllers. They expand the computer's capabilities and allow for greater flexibility in how the system is used. Direct Memory Access, or DMA, allows certain hardware subsystems to access main memory independently of the CPU. This speeds up data transfer and frees the CPU to perform other tasks, improving overall system efficiency. Interrupts are signals that temporarily halt the CPU's current operations, allowing it to respond to urgent tasks. They are essential for multitasking and real-time processing, ensuring that important events are handled promptly. To sum up, digital computers are organized into several functional units, each with a specific role. From processing and memory to input, output, and communication, these units work together to deliver the seamless computing experience we rely on every day. Understanding these units helps demystify how computers operate and highlights the importance of each component. As technology evolves, the organization and capabilities of functional units continue to advance. Innovations like multi-core processors, advanced memory hierarchies, and specialized accelerators are shaping the future of computing. Staying informed about these changes will help you better understand and leverage the power of digital computers.